Now that we know the squeeze theorem, we want to see an example of it. We haven't really done a whole lot of trigonometric limits, so we're going to get some experience with that. Squeeze theorem is not easy to use, but there are two special trig limits that we're actually going to need to help us evaluate other trigonometric limits. And these two trig limits can be proved using the squeeze theorem. And we can prove them other ways. Something you'll learn later on in calculus called L'Hopital's rule. And that's probably an easier way to prove these two limits, but we don't have that right now. So the squeeze theorem is the way we're going to do it. But really, there's two reasons for giving these examples. One, we can see an example of the squeeze theorem. And two, these two limits will help us do other trigonometric limits. Okay, so let's look at this first one. Okay. The limit as x approaches 0 of sine x over x equals 1. So this is a tricky limit because if x approaches 0, we can't just plug 0 in here for x and 0 in here for x. Because what happens is we end up getting one of those 0 over 0 indeterminate forms. Because the sign of 0 is 0, and obviously the denominator here would be 0. And so we know that that doesn't really tell us anything other than we can't plug 0 in for x. So how does this limit actually equal 1? And think about some of the other tricks that we've learned along the way we can't really use, like factoring, rationalizing. None of that really applies to this limit. So it's going to be squeeze theorem, the way you kind of get it done right now. And so what we're going to do is we're going to look at a couple of functions. First function we're going to look at is going to be your cosine of x function. Another function we're going to look at is sine x over x, and the last one is going to be 1. Well, I actually have the graph of each one of these listed right here. Cosine x is this one right there. Okay, it's your basic cosine function. It's a wave pattern. I only have it window, in this sort of space between -1 and 1, and I don't need the whole window because we're only talking about getting close to 0, so we just need to see what it looks like close to 0. And so you see that we have that function there. And 1, I also have that drawn. Okay, that one is this horizontal line. Okay, that's y equals 1. All right. And so you see cosine x is the smaller function. It's the one on the bottom. 1 is the top function this entire time in this window. It's a bigger function. And believe it or not, sine x over x, if I was to graph that, is this middle function. And you see that sine x over x is squeezed in between the two of them. And so the idea here is we have this inequality set up, okay, where cosine x is smaller than or equal to sine x, which is smaller than or equal to 1 in this interval around 0 here. All right. Well, I can do the limit as x approaches 0 of cosine x. Okay? And I can do the limit as x approaches 0 of 1. Those are actually really easy limits. This is actually one we could just plug x right in because cosine of 0 is 1. Okay, so that limit equals 1. And this is the limit of a constant. The limit of a constant is always that constant, so that's 1. Well, what do we have? We have this inequality set up the way we want it. We can find the limit of this function, and we get 1. We can find the limit of this function, and we get 1. They happen to be the same. Therefore, by the squeeze theorem, the limit as x approaches 0 of sine x over x also has to equal 1. And that's an application of the squeeze theorem. Now, everyone always asks, well, where did you come up with cosine x and 1? And how did you know that it's inequality? Well, I mean, it's not the easiest thing to come up with these functions. And that's the tricky part about the squeeze theorem, is how do you do that? And so we can look at some triangles and some areas of triangles to help us do this. Right now, all I wanted to get you is, an example of the squeeze theorem applying and seeing that it actually works. But that's the problem with the squeeze theorem, is coming up with these other functions that we're going to use in the squeeze theorem oftentimes comes out of left field. It really comes from just working with different functions and trying to find ones that will give you what you're looking for. So anyway, I want you to commit these two limits, okay, to memory so that we don't have to go through and prove them over and over again. Because what we're going to be able to do is use them to do other limits, to show the value of other limits. This other limit here, limit as x approaches 0 of 1 minus cosine x over x, it generally kind of proves a lot the same way. Right now I want to just jump into using them. So here's a very easy example. All right, so we want to do the limit as x approaches 0 of this function. Okay. Now here's the problem. If x was 0, clearly 0 in the denominator, major issue. But if I plug 0 elsewhere, what happens is the numerator gets 0. So this thing is going to that 0 over 0 limit. So indeterminate doesn't really tell us a whole lot. Figure out another way to do it. Factoring is not going to do a whole lot, rationalizing, canceling. But what we're going to do is break this apart. So I'm going to write this as the limit as x approaches 0 of sine x over x times 1 minus cosine x over x. It's still the same thing. This is still x squared in the denominator. This is sine x times 1 minus cosine x. But we have this rule that says we could take the limit of each piece of a product separately as long as each limit exists, okay? And we don't end up with an undefined value. So here we can do is do the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 minus cosine x over x. And it just so happens each one of these is one of those special trigonometric limits we just got done talking about. We just proved that this one equals 1, and we didn't prove this one, but this one, if you remember back to the previous slide, equals 0. And therefore 1 times 0 is 0. So by knowing what each one of these pieces is, okay, we can use those to help us do other trigonometric limits. And for right now, this is largely the way you're going to do a lot of trigonometric limits. All right, here's another one. So, first, if x was 0, problem, 0 in the denominator. Also, x is 0 here, tan of 0 is 0, so this is one of those indeterminate limits. So what are we going to do? What we're going to do is we're going to find another way to work with this. Well, what I want to do is basically try and use one of these two limits, if not both of them. The limit as x approaches 0 of sine x over x equals 1, or the limit as x approaches 0 of 1 minus cosine x over x equals 0. Okay, I want to use each of those. And so how are we going to do this? Well, we're going to have to mess around with some trig identities and use these. And really, we're going to end up using this one. So a couple of things here. First, I'm going to multiply this fraction by 5 over 5. Okay? Mainly because I want this 5x to be down here, and so that I can use this limit here. All right. So what I have is the limit as x approaches 0 of 5 times tan 5x over 5x. Okay. Then I'm going to break my tangent apart. Tangent we know is sine over cosine. So then I'm going to say, all right, well, this is the limit as x approaches 0 of 5 times sine 5x over cosine 5x all over 5x. Okay? Then I'm going to break this apart even further and write this as the limit as x approaches 0 of 5 times sine 5x over 5x times 1 over cosine 5x. Okay? And so, same idea here. I have a bunch of things multiplied together. This is a constant. Limit of a constant will be a constant. This is actually using this. Okay? And then here is another function. As long as the denominator doesn't give a 0, this thing is not undefined, indeterminate, whatever, we can break each one of these apart and use the individual limits to find the limit of the whole thing. So if I do that, I have the limit as x approaches 0 of 5 times the limit as x approaches 0 of sine 5x over 5x times the limit as x approaches 0 of 1 over cosine 5x. And so, like we said a second ago, this one will just be the 5 times this, we know, equals 1, okay? And this, if x is 0, cosine of 0 is 1, and so that's 1 as well. So what do we get out of this whole thing? 5. So the limit of this function is 5. Now there's a really important thing here, is that this limit, we needed that extra 5 in the denominator. Because if I'm doing the limit as, let's say, theta approaches 0 of sine theta over theta. I'm just going to use thetas instead of x's. The key to this is that this and this are the same and are doing the same thing, because that has to be the thing that's going to 0 for this limit to apply. If I had 5 theta, if I have the limit as theta goes to 0 of sine of 5 theta over theta, that's not the same. Sine of 5 theta and sine of theta are not necessarily the same. And so whatever I'm taking the sine of here has to be what's also in the denominator here for this limit to apply, which is why I needed that extra 5. And so that's why I multiplied by 5 over 5 there, so that I could use this limit that we have to evaluate this middle piece. Because really, it wouldn't apply if the 5 was only inside the sine function. And it made a difference too, because then it gave us this extra 5 here, which really made the limit equal 5. And so make sure that when you're applying one of these two limits, you're applying it exactly as it is stated. If it's a variation of one of those, it may not apply. So here's two special trig limits, this one and this one, that we can use to help us evaluate other trig limits if we can turn our trig functions into one of these two. Later in your calculus career, you'll have easier ways of working with trigonometric limits. Like I said, there's something called L'Hopital's rule that you'll learn, which really makes things a lot easier. The more you learn about derivatives, which will be a concept you'll see in a little bit, it makes this idea of limits a little bit easier. But for right now, with our limited scope that we have to work with, this is the primary way you're going to work with trigonometric limits.